Welcome to our deep dive into rotational dynamics. In this video, we'll explore the fascinating world of objects in rotation, uncovering the principles that govern spinning tops, wheels, and even planets. Rotational dynamics is a branch of physics that deals with the motion of objects as they rotate about an axis. Just as linear dynamics explains how objects move in a straight line, rotational dynamics helps us understand how and why things spin. Whether you're curious about the science behind a figure skater's spin or the engineering of a car's wheels, this journey will illuminate the forces and laws at play. Let's get started by laying the groundwork for what rotational dynamics really means. Rotation occurs when an object turns around an internal axis. Think of the Earth spinning on its axis or a spinning top twirling on the floor. Unlike linear motion where objects move from one place to another, rotation is all about movement around a fixed point. This distinction is crucial in physics because the forces and equations involved are different. Understanding rotation helps us analyze everything from the motion of planets to the gears in a clock. As we move forward, keep in mind that rotational motion is everywhere in our daily lives, often in places we might not immediately notice. The axis of rotation is the imaginary line around which an object spins. For example, when a wheel turns, its axis runs through the center. The Earth's axis is tilted, which is why we have seasons. Understanding the axis is key to analyzing rotational motion as it determines how the object moves and how forces act upon it. In engineering, the placement of the axis can affect the stability and efficiency of machines. Whether it's a gymnast performing a flip or a wind turbine generating power, the axis of rotation is always at the heart of the action. Angular displacement measures how much an object has rotated, typically in degrees or radians. Imagine turning a doorknob. The angle it turns through is its angular displacement. This concept is similar to distance in linear motion but applies to rotation. It helps us quantify how far something has spun from its starting position. In sports, for example, a diver's twist or a gymnast's somersault can be described using angular displacement. Understanding this measurement is essential for analyzing and predicting rotational movement in both natural and engineered systems. Angular velocity tells us how fast something is spinning. It's measured in radians per second or degrees per second. For example, when you spin a bicycle wheel, the rate at which it completes each turn is its angular velocity. This is a key concept in rotational dynamics because it helps us compare the speed of different rotating objects. Whether it's a record player spinning a vinyl or the blades of a helicopter, angular velocity gives us a way to describe and analyze their motion. It's a fundamental building block for understanding more complex rotational behaviors. Angular acceleration measures how quickly the angular velocity of an object changes. If you spin a merry-go-round faster and faster, you're increasing its angular acceleration. This concept is important for understanding how objects speed up or slow down in rotation. In engineering, controlling angular acceleration is crucial for safety and performance, such as in car engines or amusement park rides. By studying angular acceleration, we can predict how objects will respond to forces and design systems that operate smoothly and efficiently. Torque is the force that causes objects to rotate. Think of using a wrench to loosen a bolt. The harder you push, the more torque you apply. Torque depends on both the force applied and the distance from the axis of rotation. It's measured in Newton meters. In everyday life, torque is what lets us open doors, ride bicycles, and even turn steering wheels. Understanding torque is essential for analyzing how forces create rotation and for designing tools and machines that make our lives easier. Moment of inertia is a measure of how difficult it is to change an object's rotational motion. It depends on the mass of the object and how that mass is distributed relative to the axis of rotation. For example, it's easier to spin a pencil than a heavy flywheel because the flywheel has a much larger moment of inertia. This concept is crucial in engineering and physics, helping us design everything from car wheels to spinning satellites. By understanding moment of inertia, we can predict how objects will respond to forces and design systems for stability and efficiency. Newton's second law, which relates force and acceleration, also applies to rotation. In rotational dynamics, it states that the torque on an object equals its moment of inertia times its angular acceleration. This law helps us predict how objects will spin when forces are applied. For example, if you apply more torque to a wheel, it will spin faster depending on its moment of inertia. This principle is fundamental in engineering, from designing engines to understanding how athletes perform spins and flips. Angular momentum is a property of rotating objects that is conserved unless acted on by an external torque. This means that if no outside forces interfere, a spinning object will keep spinning at the same rate. Figure skaters use this principle when they pull their arms in to spin faster. Conservation of angular momentum is a powerful concept in physics, explaining everything from the motion of planets to the tricks performed by athletes. It's a key reason why rotational motion can be so stable and predictable. Let's look at a figure skater spinning on the ice. When the skater pulls their arms in, they spin faster. This happens because pulling in the arms reduces the moment of inertia, so the angular velocity increases to conserve angular momentum. This real-world example beautifully demonstrates the principles of rotational dynamics in action. It shows how changing the distribution of mass affects rotation, and why understanding these concepts is so important in sports and engineering. Rotational kinetic energy is the energy an object has due to its rotation. It depends on both the moment of inertia and the angular velocity. For example, a spinning flywheel stores energy that can be used to power machines. This concept is important in many fields, from automotive engineering to renewable energy. By understanding rotational kinetic energy, we can design systems that store and use energy more efficiently, making technology safer and more effective. Just as in linear motion, work and power are important in rotational dynamics. Work is done when a torque causes an object to rotate through an angle. Power measures how quickly this work is done. For example, when you pedal a bicycle, you're doing work to turn the wheels, and the faster you pedal, the more power you generate. Understanding work and power in rotation helps engineers design more efficient machines and athletes optimize their performance. Centripetal force is the inward force that keeps an object moving in a circular path. For example, when you swing a ball on a string, the tension in the string provides the centripetal force. Without this force, the object would fly off in a straight line. Centripetal force is essential for understanding the motion of planets, cars turning corners, and even amusement park rides. It's a key concept in both linear and rotational dynamics. Gyroscopic effect is the tendency of a spinning object to maintain its orientation. This is why spinning tops stay upright and why bicycles are easier to balance when moving. The gyroscopic effect is used in navigation systems, spacecraft, and even smartphones. Understanding this phenomenon helps engineers design stable vehicles and devices. It's a fascinating example of how rotational dynamics can be harnessed for practical application. Precession is the slow change in the orientation of the axis of a spinning object. For example, the wobble of a spinning top or the slow shift in the Earth's axis over thousands of years. Precession is caused by external forces acting on the spinning object. This concept is important in astronomy, engineering, and navigation. By understanding precession, we can predict and control the behavior of rotating systems, from satellites to gyroscope. Rolling motion combines both rotation and translation. When a wheel rolls down a hill, it spins around its axis while also moving forward. This type of motion is common in everyday life, from cars driving on roads to balls rolling across the floor. Understanding rolling motion helps engineers design better vehicles and athletes improve their techniques. It's a perfect example of how rotational and linear dynamics work together. Friction plays a crucial role in rotational motion. It can slow down spinning objects or help them grip surfaces. For example, the friction between car tires and the road allows vehicles to turn corners safely. In machines, managing friction is essential for efficiency and longevity. By understanding how friction affects rotation, engineers can design systems that minimize energy loss and maximize performance. Rotational equilibrium occurs when the sum of all torques acting on an object is zero. In this state, the object either remains at rest or continues spinning at a constant rate. Balancing a seesaw or a mobile hanging from the ceiling are examples of rotational equilibrium. This concept is important in engineering and architecture, ensuring that structures and machines remain stable and safe under various forces. Rotational dynamics is at the heart of many engineering applications. From designing car engines to building wind turbines, understanding how objects spin and respond to forces is essential. Engineers use the principles of rotational dynamics to create efficient, safe, and reliable machines. Whether it's optimizing the performance of a jet engine or ensuring the stability of a bridge, rotational dynamics provides the tools and knowledge needed for innovation. Nature is full of examples of rotational motion. The Earth rotates on its axis, causing day and night. Hurricanes spin due to the Coriolis effect. Even galaxies rotate, shaping the structure of the universe. By studying rotational dynamics, scientists can better understand natural phenomena and predict their behavior. This knowledge helps us prepare for natural disasters and explore the mysteries of the cosmos. Athletes use rotational dynamics to enhance their performance. Gymnasts, divers, and figure skaters all rely on spinning and twisting to execute complex moves. Understanding how to control angular momentum and torque allows athletes to perform with precision and grace. Coaches use these principles to train athletes and improve their techniques, making rotational dynamics a key part of sports science. Space, rotational dynamics plays a vital role in the movement of satellites, planets, and spacecraft. Engineers must account for rotational motion when designing and controlling these objects. For example, satellites use gyroscopes to maintain orientation, and astronauts use rotational dynamics to maneuver in zero gravity. Understanding these principles is essential for space exploration and technology. Rotational dynamics isn't just for scientists and engineers, it's part of our daily lives. From turning doorknobs and riding bicycles to using kitchen appliances, we encounter rotational motion constantly. Understanding these principles can help us use tools more effectively and appreciate the science behind everyday activities. It's a reminder that physics is all around us, shaping the way we live and interact with the world. Modern technology relies heavily on rotational dynamics. Hard drives, electric motors, and turbines all use spinning components to function. Engineers use the principles of rotational motion to design faster, more efficient, and more reliable devices. By mastering rotational dynamics, we can continue to innovate and create new technologies that improve our lives. Transportation systems depend on rotational dynamics. Wheels, gears, and engines all involve spinning parts. Understanding how these components work allows engineers to design safer, more efficient vehicles. From bicycles to airplanes, rotational motion is at the core of how we move people and goods around the world. Machines of all kinds use rotational dynamics to perform work. From washing machines to wind turbines, spinning parts are essential for operation. Engineers analyze rotational motion to optimize performance, reduce wear and tear, and ensure safety. Understanding these principles is key to designing reliable and effective machines. Construction equipment, such as cranes and drills, uses rotational dynamics to lift, move, and shape materials. Understanding how torque and moment of inertia affect these machines helps engineers design safer and more efficient construction processes. Rotational dynamics ensures that heavy loads can be moved with precision and stability. Robots often use rotating joints and wheels to move and manipulate objects. Engineers apply the principles of rotational dynamics to design robots that are agile, precise, and efficient. By understanding how torque, angular velocity, and moment of inertia interact, robotic systems can perform complex tasks with accuracy and speed. Medical devices, such as centrifuges and MRI machines, use rotational motion to analyze samples and create images. Understanding rotational dynamics allows engineers and doctors to design safer, more effective equipment. These technologies have revolutionized healthcare, making diagnosis and treatment more accurate and accessible. Entertainment devices like record players and amusement park rides rely on rotational dynamics for fun and excitement. Understanding how these systems work ensures safety and enhances the experience. Engineers use rotational dynamics to design rides that are thrilling yet secure and to create devices that deliver high-quality sound and visuals. Artists use rotational motion in sculptures, installations, and kinetic art. Spinning elements can create mesmerizing visual effects and bring art to life. Understanding the physics behind these movements allows artists to push the boundaries of creativity and design pieces that captivate audiences. Agricultural machines such as tractors and harvesters use rotating blades and wheels to plant, harvest, and process crops. Engineers apply rotational dynamics to design equipment that is efficient, durable, and safe. This technology has transformed agriculture, increasing productivity and reducing manual labor. Wind turbines and hydroelectric generators use rotational motion to produce clean energy. By understanding how to maximize torque and efficiency, engineers can design systems that harness natural forces to power our world. Rotational dynamics is at the forefront of the renewable energy revolution, helping us build a more sustainable future. Manufacturing processes often involve rotating tools and machines, such as lathes and drills. Understanding rotational dynamics helps engineers optimize production, reduce waste, and improve safety. By mastering these principles, manufacturers can create high-quality products efficiently and reliably. Kitchen appliances like blenders, mixers, and food processors use rotational motion to chop, mix, and blend ingredients. Understanding the physics behind these devices allows for better design and improved performance. Rotational dynamics makes food preparation faster, easier, and more enjoyable. Many toys, from spinning tops to remote-controlled cars, use rotational motion for fun and entertainment. Understanding how these toys work can inspire curiosity and learning in children. Rotational dynamics brings play to life, making toys more engaging and educational. Musical instruments like drums and turntables use rotational motion to create sound. Understanding the physics of rotation helps musicians and engineers design instruments that produce richer, more dynamic music. Rotational dynamics adds a new dimension to the art of sound. Fashion designers use rotational motion in spinning looms and sewing machines to create fabrics and garments. Understanding these processes allows for more efficient production and innovative designs. Rotational dynamics is woven into the fabric of the fashion industry, driving creativity and efficiency. Communication devices, such as hard drives and satellite dishes, use rotational motion to store data and transmit signals. Engineers use the principles of rotational dynamics to design faster, more reliable communication systems. This technology keeps us connected in our digital world. Security systems, such as surveillance cameras, often use rotational motion to scan and monitor areas. Understanding how to control and optimize this motion ensures comprehensive coverage and reliable operation. Rotational dynamics helps keep our homes and businesses safe. Scientists use rotational dynamics to study everything from atoms to galaxies. By understanding how objects spin and interact, researchers can unlock the secrets of the universe. Rotational dynamics is a powerful tool for discovery, driving progress in physics, chemistry, and astronomy. Teachers use demonstrations and experiments involving rotational motion to engage students and explain complex concepts. By making learning interactive and hands-on, rotational dynamics becomes more accessible and enjoyable. This approach inspires the next generation of scientists and engineers. Throughout history, inventors and scientists have used rotational dynamics to solve problems and create new technologies. From the invention of the wheel to the development of modern engines, understanding how things spin has driven human progress. Studying the history of rotational dynamics reveals the impact of this field on our world. We've explored the core concepts and real-world applications of rotational dynamics, from the basics of angular velocity and torque to their role in technology, nature, and everyday life. Understanding rotational dynamics not only deepens our appreciation for the world around us, but also empowers us to innovate and solve problems. Whether you're a student, engineer, or simply curious, the principles of rotational motion are essential knowledge. Thanks for joining this journey through the science of spinning objects.